coming. I'm pleased to introduce Rustan Leino as our Informatics Distinguished Lecturer. He's going to be talking about program verification. Rustan's well known in the software verification community for his long-standing program of bringing software specification and automated verification to the masses, really. First at DEC SRC and then Compaq. He was responsible for the ESC Java extended statics checker for the Java programming language, which allows programmers to make assertions about Java programs and have these automatically verified or not, giving back information about the correctness or otherwise of their programs. He's now at Microsoft Research at Redmond, where he's been responsible for the Spec Sharp tool, which does similar things to C#, and also the Boogie framework underlying a whole range of program verification environments. And throughout all of this, he's done a lot on bridging the gap between programmer-accessible integrated development environments for specifying programs and connecting those to some really very sophisticated automated proof tools and decision engines, and making it possible for programmers to use those in their everyday work. And as well as developing tools for this and implementing them and selling them to people, he's something of an evangelist for improving programming, and indeed programmers, through getting them to use these tools and to change the way they write programs and what the programs that come out of that. So today he's going to be talking about the past, present, and future of software verification, and Rustan.
All right, thank you very much. It was fun to walk the streets yesterday of Edinburgh and look at all of the kilt stores and so forth. Last week I was with my computer scientist child who's going to go to college next year, and we were visiting CMU, which also has plaid as its school colors. So I was thinking, here's another school with plaid as its color. What's the deal, right? Anyhow, okay, what I'm going to tell you about is, as computer scientists, we know that half-open intervals are the thing to be going with. But today I'm actually going to talk about something that's open on both ends here. And I thought I'd give you just a little bit of introduction to program verification, the way that I've used the technology. Now, there's a lot more to say about it, so this will be from my perspective. Give you just a flavor of some of the tools in use today, and again, that will be biased from my view of them, and then give you a little bit of an idea of where at least I'm going next in my research and other people have done. Okay, so there are a bunch of things that we want from software engineering when we do software development, and we'd like to develop programs that have the right features. That is that they do the right sorts of things for the users, and we want them to be easy to use so that you can easily get out of the programs what you want them to do. And the flip side of that is that you want them to be hard to misuse. For example, you don't want them to be accidentally misused. That you spell check your document and you press some button and you delete your contents of your disk, for example, but at the same time you also want to prevent malicious misuse of your programs, that is in various security attacks and things like that. Something else that's very important for the developer of the software is that you can develop it effectively. That is, that you can get out there and meet the deadlines that you're looking at, and you'd like it to be as error-free as the market demands. And that does not usually mean that it's totally free of errors, but that it's enough free of errors that people would pay for it. That is, if you made it even better, that it might be too expensive for the users, and that depends on the area. If you're looking at dancing clowns on the web page, the price you would pay for correctness is very low, for example. Okay, and something else that's important for the developer is that the code is going to be maintainable in some way. And maintainable, what that means is that you should be able to add features to it. You should be able to adjust to new environment, new drivers, new driver models, things like that. And something that's very important is when you've written a piece of software, a few months later you go back to it to either fix some bugs or add some features, or a new person comes into your development team and you'd like to be able to transfer that knowledge that you had at some point in time to the new developers. And that can also be a very costly endeavor. So these are many things that we want from software, and I can't talk about all of them, but I'll focus on some parts of it that have to do with the correctness angle of it. And to do that, we're going to reason about the programs in some way. So what you need to reason about programs is you need the program semantics in some form. You need some idea of what it is that you're going to check about the program, some form of specifications or contracts, as they're also called, which may come from the programmer, may come from a library developer, may come from the language designer. And then you want some tools to plug into the chain that actually do something for you. If you just have two of the three, you're really not doing as well as if you have the whole chain here. Okay, so what I'm going to do then is I'm going to tell you a little bit about the history or some of the movements leading up to where we are today. So I'll call that yesterday, even though this technology is still used today. So but it's work that has been done before. Okay, so let's start with Floyd. What doesn't start there, perhaps? But so Floyd considered many years ago flow graphs, or as some people call them, flaw graphs, of programs. And the idea that he had for reasoning about the program is that if you have a flow graph, what you can do is you can label each edge with some predicate, that is, some description of the state space at the time that the edge is traversed. So if you take this little program and you decorate it with these labels, what you find is that if the program begins in a state where n is at least 0, and you follow the flow graph, no matter where you go, whenever you travel across an edge, that condition holds. So that says that if you ever get out of this loop, then we get down here and r and n stand in that relation, which says, if you can read it from the back, that r is the integer square root of n in this case. So that's one way to reason about programs. And this made a difference in that we could actually start to think about portions of the program and reason about each step of the program to reason about the full correctness of the whole thing. Okay, then came Hor and liked this idea and developed it into logic, which I think is a really good thing to do for a lot of reasoning techniques that we've seen. That is, if you can bake them into logic and present it to people, that seems to be a good idea. So here's a Hor Triple. So the Hor Triple has, Hor didn't call them that to begin with, but that's what we call them now. You have three components to it. You have a program that sits in the middle, S, and you have two predicates, that is, two descriptions of the state space in some way, P and Q. And those are well, predicates, assertions, specifications, whatever you'd like to call them. And now what this means is that if you start the program in a state satisfying P and you run it, then all of the outcomes of the program satisfy Q. So this gives you a precondition and a postcondition and into a triple. So if we take the little program that we had on the previous slide here, if you write it more in a Pascal-like language, it looks something like this. And you can then decorate it with the same, with Floyd's sort of edges, but you write them as little assertions or as comments throughout the program. And one of the important things that came out of the Hor logic, which was formalized more clearly there than in what you see for all of the edges in the flow graph, is the concept of an invariant, in this case a loop invariant. That is, if you have a loop and you want to reason about the loop, if you can find a condition that holds on entering the loop, and you can prove that it holds again after each iteration, assuming that it holds at the beginning of each iteration, then you can do a kind of inductive proof that you do in mathematics, for example, proving theorems inductively as well. So let me show you what that might look like in a program editor. So if so here's that same program, and you can see that I decorated the program with an invariant and an assertion at the end, but I left out all of the intermediate assertions that say something just before the loop and so forth, because those are checked automatically. So if I change this program in some sort of way, for example, updating r here by 2, I get some violation of some part of either the annotations, well, of the annotations that I gave it, or maybe some rule of the programming language that say that I've done something bad, like maybe index an array outside its bounds. Okay, that gives you a little bit of a flavor of putting that into an editor. Okay, so after the Hor logic, Dijkstra formulated the, well, you might say the same thing, in a different kind of calculational way, which was to say that anytime that we have a triple, or for that matter, any kind of tuple, but if you have a triple like this, you could consider removing one of the parts. You could consider removing the program, that is, for a P and a Q, what are all of the programs that you can put in between? But Dijkstra at this point considered the possibility of removing either the P or the Q. And he said that the strongest postcondition given P and S is the strongest Q that you can put in and still make the Hor triple work. So in other words, it's the strongest characterization that you can make, the most that you can say about the post state that you're guaranteed. And going the other way, if you remove the P and you say what is the weakest P, that is, what's the most general thing that you can say of a pre-state so that executing S from that pre-state will take you to Q, that's called the weakest precondition. And this has several advantages over the Hor triples. One is that you can represent the Hor triples as either of these two formulas. You can say that the strongest postcondition implies Q or that P implies the weakest precondition. And that's the same, either one of these is the same as that Hor triple if you talk about the right semantics, that if you look at termination or not, or whichever semantics you're looking at. But it also made non-determinism quite easy to reason about, which it also is in Hor triples. But especially when you calculate weakest preconditions, dealing with non-determinism is of no extra cost. That is, you can easily deal with non-deterministic programs, and that's quite important when you reason with specifications, because when you specify a program, you tend to underspecify it, leaving room for the implementation to do specific things. And one thing that matters the most for when you build a program checker is that you can actually calculate the conditions. So whereas Floyd needed a condition on every edge, and the Hor triples say something at every semicolon, for example, if you used weakest preconditions or strongest postconditions, you can just calculate what all those conditions are. So you just need additional explicit conditions at, for example, call sites or at loop boundaries. And that's important. Okay, so I think what happened in the 70s, which I wasn't much into computer science at that point myself, was more into building Legos, perhaps, maybe, but I think there was a movement of striving for a scientific ideal, trying to really prove every program correct and getting rid of all errors. And I think what we've learned since then, in fact, several decades ago, was that's really just a scientific ideal. It's a good ideal to strive for, but we won't really get there. And it's any kind of verification that we do is always going to be at some level of abstraction. So even if we prove that a Pascal program is entirely correct, we still have the compiler, we still have the machine that could go wrong, hardware that could fail in some way, or gamma rays, or any kind of disturbance to the whole thing. So we're verifying things at a particular level of abstraction. But that's not to underestimate what that could mean, because a programmer today, when you test the program, you test it in a particular environment. So that's also testing it at some level of abstraction. Okay, so what are some things that made this into an engineering reality? Well, one thing, as I said, is being able to compute weakest preconditions. I think it helps a lot. But then there were a number of people who worked on techniques that helped us build tools. Here's one of them, and I'll just show a few of them again. And it's Jim King's symbolic execution, which said that when you execute a program, here he also used flow graphs, you can, instead of actually pushing individual values for the variables, you just push conditions symbolically ahead. So here, if we have a test of x being less than 0, if you go that way, we know x is less than 0, otherwise we know it's at least 0. And we can push that ahead, and then when we come to a join point, we have either the left or the right, which in this case turns out to be proving that you have the absolute value of x. This seems like a very nice technique, because you can execute the programs going forward and do it not just for one value at a time, but lots of values. But loops are a problem when you do symbolic execution, or for that matter, when you do any kind of analysis. So one attack on loops is that presented by the Cousseaus in the 70s. And they said that if you step through a program like this and you do symbolic execution, you might might find that n is 0 here, and then you take another round through the loop. You notice it could be either 0 or 1, and you continue like that, and you get a bunch of different values, and this would not end. So in abstract interpretation, you take all of those together, and at some point you decide you're going to give up. This does not look like it's going to converge to just one nice predicate. You're not going to reach a fixed point without doing something else. So you do an abstraction step or a widening step, and you replace all of that by some predicate that entails all of those. For example, that n is at least 0. And if you do that right, you get the conditions that you want to be able to prove the program correct. And other than that, once you get these things, the verification techniques are the same as in the other approaches. Okay, on the decision procedure side, that is when you reason about the programs, you're going to have to reason about if one predicate implies another, for example. And one technique that is one that has been a big part of the verifiers that I've built was developed by Greg Nelson in his PhD thesis, which was to consider cooperating decision procedures. What that means is that if you have a complete decision procedure for one theory, for example, the theory of linear arithmetic, and you have another complete decision procedure for another theory, for example, that of uninterpreted function symbols, you can combine them in a particular way. So what's called the Nelson-Oppen cooperating decision procedures is really a protocol that's used between different decision procedures in such a way that they can communicate with each other and still be a complete decision procedure. That is, that you can infer everything that could be inferred. Greg Nelson, in his thesis, also mentioned some ideas for how to instantiate quantifiers, which was not really used so much at that point, but has been used quite a bit in the 90s and all of the 2000s. Okay, a final thing that I'll like to mention as part of technology from the past is the using specifications in the programming language. So this was done in the 1970s in the Gypsy language, for example, but I think that what really popularized it was Bertrand Meyer in his move toward using contracts in object-oriented programs. So here's a little snippet of Eiffel code that you can give some pre- and post conditions as part of the program text. And I think that when you use a programming language, if you have specification constructs in the language, it feels very different than if you have to write specifications as some sort of external tool that you're going to, some auxiliary file that you're going to run as part of some testing process later. And so what we get there is we get method preconditions and method postconditions. So method precondition or procedure post precondition is a condition that you intend to hold every time that the procedure is called. And it's the caller's responsibility to establish that condition. And having that line to say that it's a caller's responsibility is a big thing when you reason about programs modularly, because you know what you can assume and what you should check when. And the postcondition is just the other way around, it's the implementation's responsibility to live up to it, and then the caller can assume it. So with all of these different things, these pieces of technology fit together, and we can build various tools using them. So what I'd like to do in just one slide here is give you 4 examples of techniques, verification tools, or tools based on verification technology that are used today at Microsoft. And these 4 are going to be ones that are used at a large scale, each one of them. It's not just small isolated instances, but they're used for lots of lines of code. Okay, the first one I'd like to mention of these 4 is the static driver verifier, which a number of years ago was called the SLAM project, done by Tom Ball and Sriram Rajamani and friends. And this, I think, was a smashing success in that they started with a research project and built it into something that then, to begin with, was cobbled together with many different tools and techniques, and that has become much more fine-tuned at this point, to the point where it's actually, the tool is, the static driver verifier is made available in the Windows device driver kit, which means that third parties can run it. Having a third party run a tool, that is, the device driver manufacturer run a tool, is quite different than having researchers in the lab run it. So this tool has gone really a long way in the last decade. And the technology, the main technology that they used was that of model checking. and they're checking device drivers from the Windows device drivers that interact with the Windows kernel. Another tool that's being used at the large scale, so by the way, I should say, but the static driver verifier is applied to all drivers that are shipped using the driver models that the tool supports. Another tool that is being used heavily at Microsoft, which is probably which is no doubt the largest application of SMT solvers in the world today, is the SAGE tool done by Patrice Godefroy and friends. And here the application is doing symbolic execution to find security holes in parsers, file parsers like JPEG parsers or similar parsers. Many of the security holes that have been found in such parsers. And you might think, well, a JPEG parser, how big could that be? Well, easily 1 million lines of code. And these things have gone through so many generations of things being added to them that no one can understand the entire code base. So what the SAGE tool does is that it performs symbolic execution, stepping through millions of instructions and calling the SMT solver, that is a decision engine in between, to try to do constraint solving. It's called it's a kind of fuzzing that's being done, and there are tons of machines at Microsoft, very large machines, very big setups running all sorts of fuzz testing, including SAGE. Okay, and a newer project has been the SimDev project, which stands for symbolic difference. Now, if you take two text files and you do a diff of the two files, you can see textually which things you changed, but you don't really know what effect that has on the program. So the symbolic difference is trying to figure out what the semantic differences between two versions of a program are. And lately, that has been applied to some what are called app compat, that is application compatibility. That is, you have different versions of a compiled program, and you're trying to compare them to see what changes you introduced. And this is using verification condition technology and the boogie tool. So what I was told recently is that SimDev applied in this way is the largest application of the boogie tool today. Okay, a fourth thing that I'd like to mention is that of code contracts. Code contracts is a little bit different from the others in that what the focus of code contracts is writing the specifications themselves. If you have a .NET program, that is a C# program, an F# program, Visual Basic, whatever it is, and you want to write specification, you can, in the style of IFL-like contracts or SpecSharp-like contracts, write them directly in your source code. And the way that this is done is that it's done using, if you're a C programmer, you might think of it as macros, but the macros do a little bit more than just expand or not expand to executable code, because you need to move post conditions, for example, to the end of the bodies to have them execute at the end. And there are a bunch of technologies, actually, a bunch of different tools that plug into the code contracts. You can get the runtime checking, you can turn off the checking altogether, you get documentation tools, there's an abstract interpreter that runs on them, and there's a very exciting testing tool called PEX that also makes use of the code contracts. And these are available for all of the .NET languages. So these are 4 examples of how formal methods or verification techniques are used at Microsoft today. So let me just show you a little bit of the code contracts, just to show you what they look like. So here's the program that I showed you before on the Floyd slide. This particular program is written in C#, and you can see, well, so you see the loop here, and here are the contracts. And what they look like, these contracts, they look just like method calls. In fact, they are method calls. So the .NET platform gives you a way to mark a method call as something that should be ignored by the compiler. So you can either ignore these and have them be here just for documentation purposes, or you can have them expand to do interesting things during the execution. Now, having these in the language, but in a language insensitive fashion is really good for making them usable. That is, when you type in one of these things, you get all of the completion that you would expect to get. For example, when I type n here, it knows that n is one of the variables. So you get the IntelliSense as you're typing in the program, and that's very useful. And it means that you can use them with any kind of .NET program. But you can also see, as I included in this, that some of the things become really clumsy. When in a post condition you want to talk about the result of something, you have to write all of that ugly thing. But this is a sort of an engineering compromise of what happened in getting these things in use. So the code contracts are shipped in .NET 4.0, and you can get the tools to run them. Let me just, if I run this little program, it ran fine here. But if I change it to, for example, pass in -10, you can see here I'm getting a precondition failure, and you'd get a similar one if where's the stop button here? If I were to if I were to stop the debugger and there it is, and change the code as such, for example. So here we get the post-condition violation. And note again that the post-condition violation actually happens at the end when we return, but it's declared up here in the beginning. So these code contracts are being used in the .NET library, that is in the implementation. So the documentation that you see generated not in previous versions, but in the future for these things actually come from contracts. And you can use them yourself. Okay, so that was yesterday. Let me say a few things about what you can do where we push the edges today. So what I've shown you is what's also being used at Microsoft today, but what where we are in the technology from the science point of view, where we push the technology, we can do quite a bit with automatic tools. So I'm going to give you one example here, and there are many other examples out there, and you may know many of them yourself. But here's an interesting spectrum that you can plot verifiers on. On the y-axis, I've plotted how much we want to verify of a program. Maybe you want to check the full functional correctness of a program, or maybe you want to do some sort of limited checking, like extended static checking. On the x-axis, I'm showing how interactive the tool is, or how automatic it is. So on the far right here, we have interactive proof assistance that you have to work to get the results. That is, you manipulate the logical formulas yourself, and that gives you lots of power to prove all sorts of things about your program. On the left-hand side, you're using automatic decision procedures like the SMT solvers today, satisfiability module theories, which is essentially what the tools that build on the Nelson-Oppen technique is more or less what that turns into. So traditional program verification lives in this corner. We're trying to prove functional correctness using interactive proof assistance. Something like extended static checking tried to use similar technology but using automatic decision procedures, but giving you only limited checking. The interesting thing here, I think, is that, so I've worked in this quadrant before, is that you can actually use automatic decision procedures in up towards the functional correctness quadrant as well, which I think is quite interesting. What that means for the programmer is that when you work at this level, you don't have to directly interact with the theorem prover. You can work at the program level and still get very high guarantees about the correctness of your program. So Daphne is one such tool, and I'm going to give you a demo of Daphne. Let me just say a few words about what Daphne is. So Daphne is a research language, but it is an actual programming language. You can write programs in it and run them. It's Java-like, if you like, or C#-like. It does not have subclassing. It does not have interfaces, but it has classes. It has dynamically allocated memory and so forth. So you could also think of it as a C program or a modern Pascal program, or if you remember the Euclid programming language, maybe this is just a better version of Euclid. With tool support. And like Eiffel and SpecSharp and others, and JML and so forth, Daphne has built-in specifications like pre and post conditions. And there are special supports in the language for writing specifications, like mathematical sets, mathematical sequences, inductive data types, and user-defined functions, which can be recursive and so forth. So you use that in the Daphne language. So let me give you a demo of the of what you can do with the language. Let's see. Here's where I want to be. So what I thought I'd do is write a little program that showcases many of the features that you have in the language. But the program is going to be very simple. So first of all, is that font okay with you in the back as well? Then I can make it bigger otherwise. Okay. So what we're going to do is a program that is given an array, and it's going to find if there's a 0 somewhere in the array. And what we're given is that the array is not null as a precondition, and also that every index in every slot in the array, the value is non-negative. So I'm going to give you one more property of the program, and that is to say that for every 2 consecutive indices, I and I plus 1, we're going to have the property that that A of I plus 1 is, actually let me write it like this. A of I plus 1 is going to be, let me split the lines here too so we can see a bit better, is going to be at most 1 from, that is, the difference between 2 consecutive elements is going to be at most 1. So let's see, did I write that correctly here? So I'm saying that if you compare A sub I and A sub I plus 1, they're at most 1 apart. Okay? So what we're now going to do is we're going to say something as a postcondition, and I'm going to talk about the output variable R, and I'm going to say that if we're returning a value that is non-negative, then the thing we're returning is indeed an index into the array, and furthermore, that index is something where we will find a 0. I'm also going to say that if we return a negative value, then there is no 0 in the array. So I'll say that as follows. Okay, are we all okay with that? So I'm going to, given arrays of that property, I'm going to write code that will satisfy that postcondition. So we can see here that we're getting some squiggly lines right away because these postconditions do not hold. And that's no surprise because we don't have any code yet. Not every program, Skip does not satisfy every specification, and this is one of those examples. Okay, so what are we going to do? Well, we're going to need a loop. So if we're going to have a loop, I just know the standard recipe for doing a loop, which looks something like this. I will have some loop variable that I will step through the bounds, the indices of the array. And I happen to know that whenever I write such a thing, I tend to do some loop invariant that says something about the bounds of the loop variable. Okay, so we want to find out something with each iteration of a loop. And what we'd like to find out is that, that out of the indices that we've gone through so far, that they are not 0. So in fact, what I'm going to do is have a loop invariant that looks very much like that. I'll copy it down to there. But instead of saying that we know that about all of the indices of the array, I'm going to say that we know it only for those indices up to n. So what do we then do in the loop? Well, we're going to check if a sub n is equal to 0, because if it is equal to 0, we can just set our output variable to that and return. And if we ever get to the end of the loop, after the loop, I will set the output variable to -1. And let's see. And with that, it proves that program is correct. So that is, I helped it along by giving it those loop invariants. But once I give it the loop invariants, it proves that program is correct. Notice that I did not go into the prover. That is, the prover is running in the background all the time. The program verifier is running. But I can concentrate on the programming concepts. I can concentrate on invariants and postconditions and think in terms of use the programmer's hat to when I think about these things. Now, I'd like to do one thing that's going to be more advanced, that's going to make this a better program, but it's going to be harder to prove, which is very often the case that if you want to write a faster program, there tends to be more to write. And so what I'm going to do now is going to be more advanced than than what I just did. And that is, well, given this property, which I haven't made use of yet, that the consecutive elements are at most 1 apart, that means that instead of just incrementing n by 1 down here, I can actually increment it by a sub n. Because if because it's going to take at least that many more array slots before we would hit a 0 in the array. So how can we convince the verifier that this is the right thing? Well, we get some complaints here. So what I'm going to show you by this demo now is essentially what you would do as the programmer as you're going through using the program verifier. We're told that this invariant might not be maintained by the loop. And in fact, if we now think about it, we're not guaranteed this anymore, because what we might be close to the end of the array and here increment n by some very large amount. So we can't maintain that loop invariant. And what I'm going to suggest is simply that we remove that loop invariant altogether. But if we remove that loop invariant, we need to think about this index, which now, if we talked about all of the indices I in that range, because n might now be very large, we might talk about something that doesn't even exist inside the array. So we'll have to do something about that. I'm going to just strengthen the antecedent here to say that we're going to look at all indices I that are less than n, and also that are less than the length of the array. Okay, so that now at least it's happy with the form of that loop invariant, but we're not yet proving that it's maintained. So how are we going to prove that it's maintained? Well, we need to prove that we can actually jump this many steps across the array. So if you start thinking about that, why is it that we can do that? Well, if we could prove, let me move it up one, if we could make use of that property of the arrays here, that adjacent elements are just 1 apart, and if we did a proof by induction, we could prove that it's okay to skip that many steps. One way to think about that is that we could sort of just virtually iterate this loop for some number of additional loop iterations, but we know we're going to do it that many times, and then just not compile it and compile it into that increment. So what I'm going to do now is I'm going to prove by induction that this thing is correct. So what I'm doing now then is more advanced than you would do for proving simpler things of a program. So I'm going to use induction. So now, usually when you do inductive proofs, you would use an interactive theorem prover, maybe Isabelle or Coq or something. But here, what I'm going to do is do the inductive proof in the program verifier in the programming language. I think it's really cool that you can do it in the language, but if you try to do hard mathematical theorems, this is not the best tool. If you could do it at all, it would be very clumsy. In those cases, definitely go to an interactive theorem prover. But here, what we're trying to do is prove a little bit of a lemma to prove the correctness of the program. So I'm going to show you that you can do that in the editor. Okay, so how am I going to even represent a lemma? Well, if I had a method, I'll call it lemma. I could formulate a postcondition of this method. Let me say, first of all, what the parameters of it are. I could formulate a postcondition of the method, because if I can give a particular property as a postcondition of the method, if the method doesn't modify anything, then what the program verifier is going to have me prove is that the thing terminates, and by the time that it terminates, the postcondition holds at the end. Which means if it didn't change anything, that it also held to begin with, so I can make use of it. So I will write that property, but I'll first copy the precondition here, because I want those same properties of the array down here. Let's see, I want those properties. I also want some property about k and m. So what I'm going to say is that if k let's see, if m is at least 0, well, maybe I would say something about the loop bounds. If k is an index, then m is a lower bound on that. How does that look? Maybe I would need an upper bound here as well. Maybe if I say that if if k is indeed an index of the array, then m is a lower bound on it. Okay? And what I'm going to ensure afterwards is that for all indices between k and k plus m, that a sub I is not a 0. Okay? And again, I'm going to run into the problem of I need that index to be an index of the array. So that's what I'd like to do. So before I fill in the body here, so it's still complaining about the postcondition not holding, let's see if this is the lemma that I need. Well, how do I make use of a lemma? Well, since it's a method, I'm just simply going to call it. I'm going to call it with the array. I'm going to call it with the current index and with the value at that point. So let's see now what happens. Yeah, I did that correctly. That was nice. So when I call a method, it's just from program verification. I know I need to live up to the precondition. So I need to pass it an array that satisfies these conditions and that also satisfies the additional ones that I put down here. Now, at the call site, I get to then assume that the postcondition holds by the time that the call returns, which is exactly the lemma that I want to prove. Okay? So now I've formulated the theorem I want to prove, so now let's prove it. Well, in many cases, the verifier might be able to prove this postcondition automatically, but not in all cases. So in particular, if m is greater than 0, and furthermore, if what do we need here? Is that well, and k is indeed less than the length of the array. That's the hard part. So what are we going to do in that case? Well, if we're going to do proof by induction, well, first of all, in that case, I believe that it's the case that a sub m is, let's see, is it equal to 0? Am I doing this right? Okay, I'm evidently not doing that right because it's complaining. Index out of range. Okay, so let's see, why did I think that? Maybe k, how about that? Okay, still complaining about that. Okay, well maybe that's, let's just still go for the inductive property, which is really the one I need. So to invoke the induction hypothesis here, I'm just going to call the lemma recursively, just like we would call a procedure recursively. I'll pass in the same array. I'll increment this because we're now going to step one step ahead. And I'm going to, oh, actually, I realized, of course, what I did wrong was a sub k is not equal to 0. That's the property that I want, of course. See if it proves that one. Yes, it proves that assertion, but does not prove the postcondition. So here we go calling this. So what I'm saying here is that if we're in this situation, then what I'd like to prove is that one step ahead, all of the elements are going to now be bounded, or that new element is going to have a lower bound of m minus 1. And that would allow me to prove it if I could prove termination. But in this case, it couldn't prove termination automatically. Often it can. So here I have to help it by saying why, by supplying a rank function or a bound function. And I'm going to say that with each call, I'm going to decrease k. Decrease m, right? There it is. That should be, there it is, right. Okay, so what I've done now is I've provided a snippet of code that every execution of this piece of code is establishing the postcondition, which is really like proving a lemma. Again, if you want to prove that for things like this, you can do it in the program verifier, and I just think that's cool. But if you do harder mathematical stuff, I mean, use a real tool for that. If you want to prove programs, use a real program verifier. If you want to prove mathematical lemmas, do them using a real theorem prover. So just in case you're wondering, and I hope you're wondering, how does Daphne work? Here's a slide that gives you the prover the verifier architecture. And it all centers around an intermediate verification language. Just like a compiler has an intermediate representation when you compile from a source language into eventually assembly, when you build a verifier, it's very useful to have an intermediate verification language. So if you build a verifier, do this as well. I mean, this is the the right thing to do, I would say. And we're using Boogie as the intermediate verification language. Boogie has a bunch of different front ends that you see here for all sorts of different languages and stuff. It has some Boogie to Boogie transformations to do inference, and it supports a number of theorem provers, although in reality, the only one that matters is Z3. Z3 is, just outdoes all of the other ones. And you can see pieces of the technology here: contracts, weakest preconditions, abstract interpretation, decision procedures. It's all technology that we use and love in there. Okay, so tomorrow I'll give a more specialized talk, and I'll tell you some about how to use Boogie. So if you're interested in that, come see that. I'd like to just point out that you could use tools like Daphne, like I just showed, in education. Talk to me if you're interested in that. Okay, so what I'm going to do now is consider the tomorrow of the whole equation, which I'll do in 5 minutes, maybe. Okay, so the idea is that when you write these specifications, like your question about what about all these specifications, do you really have to write that many lines of specification to verify a piece of code? And if you, again, I was really pushing the limit there to show that you can go all the way to prove full functional correctness. But if you do that, you have to write specs in some form. That's not how programs tend to be verified, and developed. You have some idea, you write some code, you write some tests, they go through, you ship the thing, and what about verification? Oh yes, right, you need the specification somewhere. So really what you tend to do, if you do verification at all, using the kind of tool that Daphne is, for example, it would be sort of an after-the-fact verification, and that's always painful. That's why I'm calling it post-mortem here, even, because the thing is dead already, right? You cannot go and change the whole thing. You cannot make the verification process help you design the program in a better way, because it's really too late. So that takes us to tomorrow. So what I'll do here in just a few slides is show you a research project that I've just started this spring that I'm quite excited about, and it's also using technology that's been around for some time, and ideas that have been around for a while, and trying to push the boundaries. And I'm calling it Genesis. So it's called Genesis because this is where programs begin. This is the beginning. And so what is Genesis? Well, it's like an object-oriented language or an object-based language like Daphne or Java or something like that. And the reason for that is that I think that's how programs are written. If you're writing programs for embedded software and so forth, use something else. Don't use Genesis. It probably won't be the best. I'm splitting things into 3 parts, and I'll say something about that. The public interface, the design of the data structure, and an implementation. So the public interface, here's one example. So let's consider an extensible array. So this is actually an example that a colleague brought me, but I won't have time to tell you the whole story here. I'll do it after at coffee if you want to afterwards. But the extensible array has, let's say, the following operations. So you can initialize it, you can get and set elements, and you can also make it longer by the append, which appends one operation, one element. And what I'd like to see in Genesis here is just as clean of a public interface as possible. That is, when you look at this is the specification. And the idea is that no one would want to see anything else. This is the code, if you'd like. This is how you understand what the thing does. And it should be just clean and simple. And in a case like an extensible array, which has been studied for decades, it can become clean and simple. We'll see how other examples go. The idea behind this particular implementation of extensible arrays was that you'd like to avoid copying all of the elements. So the challenge that a colleague gave me was to consider the verification of an extensible array that did not just copy everything, but where everything is, well, more or less constant time operation, more or less. Okay, let's see how we do that. So what I'm going to show you is first a picture of the data structure that I have in mind, and then show you what that looks like in Genesis. So here's the data structure. You have an extensible array object, and it's going to have as its data structure an array, a fixed size array, that is an array that's provided by the language, if you will. And when you append an element to the extensible array, you just insert it into the next slot in the array, just like you would expect. So we can do this until we've filled up the fixed size array. So now the question is, now when we've filled up the fixed size array, what are we going to do? Well, in this case, we're going to have a collection of these arrays. So when we now are going to append yet another element, we take the old one that was full, put it into that collection of arrays, allocate the new array, and then do the append into it. Okay? So as we go along here, we're going to get a bunch of different arrays in this collection. And now you start thinking, well, what about when we run out of space here? Well, it would be nice if this were a collection of some kind of form that was extensible, like an extensible array. And that's exactly what that is. So now, actually, I think that if you look at the data structure that you get from this, it's not quite a B tree, but I'm sure it has a name. But it turns out that the colleague that gave me the problem had actually hard-coded this design to like a level of, I can't remember, 3 or 4 levels down. So you had 3 and 4 levels of arrays and many complicated tests. And I tried to verify it. I guess now I am telling you the story. I tried to verify it, but when you try to verify something that's already written, it's really hard. If you want to verify something, have the verifier there from the beginning. And so at some point, I just decided that this design was the same thing really, but just much simpler, and this one I could verify. And when I gave him the verified program, he wasn't so impressed by the proof of it, because he said, I can look at this program and see directly that it's immediately that it's correct. So he just took my design and I think didn't care about the proof. He could just prove it in his head. But so at least verification did for that problem that it simplified the solution, which is good too, but often underrated. Okay, so this is the design. So how do we write that in Genesis? Well, something like this is what I have in mind, because when I wrote that program, which I did in Daphne actually, but what I spent most of my time at was designing the data structure invariant. There are many things that you could design. How that collection, for example, when should we allocate that collection? How big should that collection be? Should we, when we fill up that initial array, should we then immediately move the array into the collection and allocate a new one? Or should we lazily wait until the next time that we really are trying to append one more element? All of that comes through when you try to write the data structure invariant, which actually, let me not go into the details, but you could imagine writing some sort of invariant here, which is, in Genesis, you would write that in the model of the thing. You give the concrete variables here, and you give an invariant both of the concrete data structure and something that is a coupling invariant with the abstract. Now my hope is, and this is mostly vapor right now, except that I do actually have a parser, my hope is that the tools would be able to give you a lot of feedback on this invariant. If you're going to get anyone at all to be able to if you're going to get anyone willing at all to write down this invariant, you must provide them with some benefit. And what I'm hoping to do here is use tools that could say something like, well, you know, if this is your data structure invariant, you can't implement all operations. That would be a really good thing to know now before we've written the code for all of them, all the things. Or it might say, well, suppose that the abstract contents is 5 and the collection here has length 100, maybe with a bunch of empty arrays. Is that what we want? No, that's probably not what we want. That seems to waste space. So if the tool can detect that, maybe we can just strengthen this condition a little bit to make that a little bit better to avoid such situations. Okay, what about the code then? Well, the idea is that the code would be generated automatically. Now I realize that's a dream, and it's not always going to happen. I think that I'm optimistic that we would be able to generate the code for an example like the one I showed. But in the case that you cannot, the idea that I have for Genesis that the programmer supplies hints for maybe says, well, maybe try a loop, maybe try an assignment statements like that somewhere in the program. So this is a little bit like if you use an interactive theorem prover and you run tactics. The tactics try different things, and here I want programming tactics in a similar way. You can program with sketches or holes, which is something that Ras Burik and colleagues have tried. And as a worst resort here, you could just write the code manually. I'm just hoping that you won't have to resort to that very often. So there have been many ideas explored in this space before, like the KIDS system from the 80s. I mean, we think in the 80s, why aren't we all using that system now? And I'd like to improve on that to take their good ideas and incorporate them here to make something that more people can use. Okay, so some of the research challenges in the Genesis project are to make the public interface just as simple as you can. Try to give as much feedback as you can on the model, and try to generate as much as you can of the code. And what I'm going to target are new applications, not legacy code. If you use legacy code, use some other verification tools. This is for new stuff. But it's going to be for ones where you know it's going to be tricky up front, so that you're willing to invest your time in a new tool, and where correctness matters. If it's dancing clowns on the web page, you're probably not going to care to spend any extra time. Okay, so let me wrap up by saying that here's a website, riseforfun.com, which you can go to. So RISE is our research and software engineering group. And we have a number of the tools that we have made available online from this website. So if you want to try them out, including Daphne here, if you want to just try some Daphne programs out, you can just go to using your Windows phone, of course, or some other web browser to just try these things out. And you can also download them. So here are some URLs. You can download them and really run them in Visual Studio or from the command line, or use the mono.net distributions. You can run it under Linux or the Mac or whatever. So in summary, verification technology is being used in software development today, and it's making a difference for the kind of rigor that can be employed in the software development process. But the tools that are used today tend to be the kind where the specifications are either implicit in the language, like, for example, stepping outside the bounds of an array. That's something you can say, that's just sort of part of the language semantics. Or in the case of the device drivers, for example, there you write a little specification for a particular part of a driver that, or a particular part of an API that the driver is supposed to live up to, and you don't put specifications in the whole driver. Or in the case of SimDev that I mentioned, in that case you have two programs. So the old version of the program is the spec, and the new version of the program is trying to do something similar. So in those cases where verification technology is used, they tend to be used for specifications where there are few specifications that you have to put in. But with code contracts being used as part of development, if you think about Java doc as a tool, for example, once you start using .NET or Java, and you see all of the Java documentation being generated, you want documentation that looks like that too. So you start annotating your program with English language comments. So I'm hoping that we'll see that with the code contracts in .NET, and that people will write more contracts. We can do a lot with specifications, and the question is, should we really start with specifications? I mean, isn't that really the way that we were meant to write programs, if only the compilers were up to the task? And as I mentioned before, which I hope you'll remember, if you want to write a verifier for a programming language or a program analyzer, don't use the SMT solver directly. Use an intermediate verification language. And of course, I'd promote Boogie as that, but you can also use the competition. And as I said, here are some URLs. Thank you very much for your attention.
This production is copyright the University of Edinburgh.